Hello again, everyone. Welcome to our discussion of section 12.5, where we will talk about the principle of mathematical induction. It's basically, this is a method for proving mathematical statements, because in mathematics, a lot of axioms that we have, these were first discovered, and then they went through a rigorous proof process, and then they were established as permanent methods in mathematics for us all to use. Now, according to the syllabus at the time of recording of this video, this is the last section covered in this trigonometry class. Now, in the future, maybe a couple of years down the road, when I post this video, if there are more sections to cover, then I will be doing more videos on that. But if not, then this will be the last video for this course. And I hope you've been able to put these videos to use. Let's begin our discussion of section 12.5, or mathematical induction. We will begin with an example that tells us why we're using this mathematical induction method to begin with. So let's have a look at that. So suppose I make an obvious mathematical statement, such as, suppose I say that 1 equals 1, right? Nobody could dispute that. Everybody agrees with that, right? Then suppose I say, okay, 1 plus 3 equals 4. Okay, this is also clear. Then let me take this one step further and say that 1 plus 3 plus 5 equals 9. Okay, and so that's again pretty clear and obvious to everyone. Nobody would argue with that. And then let's say I say 1 plus 3 plus 5 plus 7, that would be 9 plus 7, 16. Again, everybody would agree with that, right? And then finally, let me make another mathematical statement. An equation is a mathematical statement. So I'm going to say that 1 plus 3 plus 5 plus 7 plus, let's say, 9 equals 25, right? Once again, nobody would argue with that. Is there anything you would notice about the numbers on the left-hand side? Is there anything particularly catching your attention in here? What do all these numbers have in common? They're all odd numbers. Not only that, they're consecutive odd numbers. So 1 plus 3, 4, 1 plus 3 plus 5, which is 5 being the next odd number after 3, and 7 being the next odd number after 5, and so on. The same thing with 9. We could keep going, but let's stop there. So on the left-hand side, here, we have, on this side, we have, so this is the, right here, we have the first odd number, right, that one. Here, we have the first two odd numbers, or right, the first two odd numbers. And we can say the same thing about all of these, that these three are the first three odd numbers, and these four are the first four odd numbers, And finally, this one is the sum of the first 5 odd numbers. Okay, that's the pattern obvious on the left-hand side. So what about the right-hand side? Do you notice any patterns on the right-hand side? Well, if you look carefully, each of these are perfect squares. Okay, so what I mean is we could write this 1 in terms of 1 squared. 1 squared is 1. 4 is 2 squared. 9 is 3 squared. So each one is a perfect square number. And 16 is 4 squared. And of course, 25 is 5 squared. Okay, so there's definitely that pattern on the right-hand side. Now, so this is, let's notice how for the first set of odd numbers, if that is equal to that number squared. For the first 2 odd numbers, if you add those first two odd numbers, then 2 squared is what they add up to. For the first 3 odd numbers, 3 squared, if you square that number 3, you get what they add up to be. And then with this one, the first four odd numbers, if you add them, they're equal to 4 squared. Very interesting, isn't it? Okay, and also for the first 5 odd numbers, they add up to another perfect square number, which is, by the way, it's the number of odd numbers added squared for all of these. That's very interesting. So with these few examples, we've shown that this is true. But suppose now I make a claim. I use these 5 examples, specific examples, to make a claim about all odd numbers. Sequentially, from the first odd number, if we add them, then we get a number that is equal to the number of odd numbers added squared. Okay, so now the question is, can we say that the above relationship or the above equations is true or are true for adding all odd numbers beginning with the first one? And so beginning with the first odd number. Right, so giving a few examples that fulfill some kind of a pattern is one thing. That's undisputable. What we have shown here cannot be disputed. It's clear. But that's one thing. Then if we say that's true for all odd numbers. So if we add the first 20 odd numbers, that is equal to 20 squared. Maybe we can show that. But what about the first 10 billion odd numbers? If we add those numbers, would they be equal to 10 billion squared? Or how about the first trillion odd numbers? If we add the first trillion odd numbers, would that be equal to 1 trillion squared? That's a different thing if we try to stretch these few examples to all odd numbers, which there are infinitely many of them. Okay, so let's ask the same question mathematically. In other words, what I've been saying about this 10 billion, a trillion, let's ask that mathematically. Asking the question mathematically, then, and using the fact that any odd number is equal to 2n minus 1, where n equals 1, 2, 3, 4, infinity, right? All the way to infinity. So any odd number can be found with this simple equation. Just substitute with n with 1 and you get 1. Substitute n with 2 and you get 3, and so on. So knowing that, then, given that any odd number can be represented with that simple expression, 2n minus 1, then we can ask, if the following infinitely many odd numbers. Okay, here's what we can state: plus dot 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 plus 2n minus 1 equals n squared. Right? We can make this statement. But how would we prove this? Because, like I said, we have, for a few examples like this, for a few examples like that, we can show it. But with 10 billion, 100 billion, 20 trillion odd numbers, or infinitely many odd numbers, that's even more important. With infinite, how can we show this? How can we make this statement and show that it's true for all infinitely many odd numbers? Or if it's not true, how can we prove or disprove this statement? Okay, so let me how can we prove or disprove this? For all the infinitely many odd numbers. How can we do that? Well, in mathematics, there are ways of proving mathematical statements just like that. There are many, many different ways of proving. And if you are a math major, when you take the 400 level real analysis course, then you'll get to see those methods in detail. At least that's the introduction. But one of those methods, which will be the topic of this section, is the induction, mathematical induction. Okay, is a one way that we can prove this statement or disprove it for all odd numbers, or for all numbers, for any numbers that would make this equation true. Okay, rather than sitting here and trying a trillion odd numbers and seeing if it will work this way, which the entire of our lifetime will not be enough for that, right? Because there are infinitely many odd numbers. Okay, so then let's look at how the mathematical induction method works. I should have called this steps to mathematical induction, or I can just call it mathematical induction steps. Like that. So for this way of proving a mathematical statement, there are 4 basic steps. So what are those steps? First one, we show statement is true for n equals 1. Okay? So we plug into this equation 1, and show that it's true for that value. It doesn't matter what kind of a mathematical statement it is. For the first value, we show that it's true. Second, so this is something we show. I should have written that in red color. And then second step is here comes the red ink, we assume that n equals some k. This is, your book calls it k, it's okay, but it's not a number, it's always a variable. And you can, and we'll do examples so you know exactly what I mean. But we'll substitute in an equation like this with the variable k. So instead of 2n, it'll be 2k minus 1 equals k squared, and so on. We'll show that would work, the equation would work for a variable like k. And well, not show, but assume. We show that it's true, the mathematical statement is true for n equals 1. We assume that it's going to work for that n equals k still holds true within the mathematical statement. And this step, it's called the induction hypothesis, or the induction step. This step is called the induction hypothesis, or induction step, or induction step. Oops. Okay, that's assumption that statement is true when we plug in k, some variable k. It's called induction step or induction hypothesis. That's what it's called. Okay. The third step, we use the assumption or use the induction hypothesis. So use the induction hypothesis to show that the mathematical statement is true for k plus 1. Okay, for n equals k plus 1. So very important, we show that the statement, mathematical statement is true for that. So that means we plug in for n with 1 and we show that the equation holds true. Then we assume that n equals k. K is not a number. It's always this variable k. You can call it m or q, whatever you like, but your book calls it k, so that's what I call it. And then use this, and then we assume that is true. We don't show this. We don't actually plug this in. We assume that this is true. Then the induction hypothesis, which is that step number 2, we use that to show that the mathematical statement is true for k plus 1, which is we plug for n with k plus 1 and show that both sides of the equation are true. And if we could do that, then that is basically the proof in the mathematical induction. So steps 1 through 3 that the mathematical statement is true for all values that are stipulated. That means this last part, that all values that are stipulated, I mean, for the example we gave here, that would be all odd numbers. Okay, that's what I mean. Okay, so let's see a couple of examples maybe. So I will go to a new page because I don't think I can fit all that here. So here we want to use mathematical induction to prove that is true for all natural numbers. Okay, so here is that statement. That is 1 plus 4 plus 7 plus that equals n times 3n minus 1 divided by 2. So this is a claim. This is an equation, mathematical statement or claim that we need to prove. That means that on the left is equal to that on the right. And we're going to use the mathematical induction to show that the left-hand side is always equal to the right-hand side for all natural numbers. Natural numbers do not include integers, right? Or negative integers. So minus 1, minus 2, minus 3. We don't have to prove that for those such numbers, but for all natural numbers. Okay, so let's begin with the induction step. Number 1, which is we show that the mathematical statement, which is that one, is true for n equals 1. So let's show that. So first step, step 1. Let's see. So for n equals 1, this is what we have. We have So this is true for -1, 2, minus. So notice these three numbers are coming from this expression. So substitute for n with 1 and you get 1. Substitute n with 2, you get 4. Substitute n with 3, you get 7. So all of this is coming from incrementing n with all natural numbers, 1, 2, 3, 4, so on, 5, so on. Okay, that's that. So all we have to show is that this is equal to that. Let's show that. So we have 3 times 1 minus 2, I'm just plugging for n with 1, is equal to, again for n, plug in with 1, 3 times 1 again, minus 1 divided by 2. What do we get? On the left we get 3 minus 2, which is 1, equals. Then what do we have? Let's make sure that we observe the order of operations. So start from inside the parentheses. 3 times 1 is 3, minus 1 is 2, 2 times 1 is 2, 2 over 2, 1. So the first step in the mathematical induction is we've been able to show that. Okay. If this doesn't work, then we can say that this does not work. This equation is not true, but it's working. So step 2 is, remember what that was? It was, we're going to assume, not show, we assume that n equals k still holds true. Okay, so step 2, assume that n equals k is true. So thus according, remember this is the induction hypothesis, right? This step. According to the induction hypothesis, we can write, and this is, we're going to assume that this is true. We're going to assume that this equation is true. Okay, all I did was replace n with k. Like I say, the author of your textbook uses k, so I'm using k, but you can use any letter. But it's not a number that you plug in like 1 or 2 or anything. It's just a variable. Let's call it k. So we assume that this is true. This equation is true. Okay. Step 3. Now we want to use this statement, use the induction hypothesis to show that n equals k plus 1 is true. So now we're not assuming anymore, we have to show. So first we show that, then we assume the induction hypothesis, then we are using the induction hypothesis to show once again that this is true. Okay, so we have to plug in and work the equation. Okay, so let's do that. So to do that, I'm going to plug in this equation with k plus 1. So k is going to go away. I'm going to plug in k plus 1 and show that both sides are equal. Okay, so let's do that. So we have 1 plus 4 plus 7 plus dot 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 plus 3k 3k minus 2, which is that, right? This piece. This is part of the induction hypothesis. We assume that this is true. So we take that piece, 3k minus 2, right? Plus, now we got to plug in this, k plus 1. So plus, so this piece, so far, this is the induction hypothesis. We assume that this is true. Induction hypothesis, right? That's from step 2, and we're using that to show that this is true. So now we have an additional term, right? 3k minus 2. Let's plug in for k with k plus 1. What do we get? We get 3k plus 1 minus 2, right? Now we do the same thing on the right. I hope I'm not running out of room there. It looks like it. So instead of k, I'm going to plug in k plus 1, right? So instead of that, k plus 1 times, in there, instead of k, k plus 1 again. 3 times k plus 1 minus 1, like that, over 2. Okay, like that. So this piece, we know it's true. We added this because this is the k plus 1 part. So then the right-hand side, again, we're plugging in for k with k plus 1. We haven't shown that this is a valid equation yet, but we're going to go through simplification process and show that. So remember this piece, the induction hypothesis? We assume that all of that, which is all of this piece, is equal to what? K times 3k minus 1 over 2. We've assumed that. So let's replace all of that with the right-hand side, which is equal to it. Okay? So using that, we will write down k times 3k minus 1 divided by 2. We're just replacing this with this. Why? Because that was our induction hypothesis. All of that is equal to k times 3k minus 1 over 2, which I replaced this with its equivalent. Okay, that's all I did. Okay, so let's now add that piece, but after we simplify it, okay? So let's simplify it too. So we have plus 3k, then 3 times 1 is 3, minus 2 is 1. 3 minus 2 is 1, right? So positive 1. So 3k plus 1. That's after we simplify this, we get this. On the right, let's also simplify that. What do we get? We get k plus 1, which is that, times, let's simplify inside the brackets. That's 3k. Then 3 times 1 is 3 minus 1 is 2, right? Because this 3 distributes itself just into these two terms, not that one. So 3 times 1 is 3, minus 1 is positive 2. So positive 2 over 2. Okay, I hope this is making sense. Okay, we're just simplifying now. We're doing the algebra after plugging in for n with k plus 1. Okay, so now let's take the common denominator on the left-hand side. So we have 2, and so this piece is the same thing, right? K times 3k minus 1 plus 2 times all of that, right? 2 times 3k plus 1 equals the other side. I'm going to keep that in factored form for now. Let's see what happens on the left, because the right-hand side is nice and neat and in factored form. The left-hand side, we got a lot of things to deal with. First, with this common denominator thing, right? 3k plus 2 divided by 2. So let's simplify this side a little more. We get k times 3k minus 1 plus, distribute the 2, we get 6k plus 2 over 2 equals k plus 1 times 3k plus 2 divided by 2. Okay, so now let's distribute the k into this. Okay, so we have 3k squared minus k plus 6k plus 2 over 2 equals k plus 1 times 3k plus 2 divided by 2. And then this is just a quadratic equation, right? So it is 3k squared minus k plus 6k. It's positive 5k plus 2 over 2 equals k plus 1 times 3k plus 2 divided by 2. Now take a look at the left-hand side. We can factor it. Factor the left-hand side, and we are able to get the same thing we have on the right-hand side, right? So we have k plus 1 times 3k plus 2. Let's see. So we have plus 2 over 2 equals k plus 1 times 3k plus 2 divided by 2, right? Just factor these two terms, this quadratic equation, and you'll get that. So now look at the left and the right-hand side. They're equal, aren't they? So we've shown by mathematical induction, so this is, proof is complete. Our proof is complete here. And of course, we use the mathematical induction. Okay? So that means this statement is proven for all natural numbers. For all natural numbers, 1, 2, 3, 4, 5, 6, and so on, this statement is true. Okay? So let's see another example. So we want to use mathematical induction to prove or show that this equation is true for all natural numbers again. This is this plus 5 cubed plus 2n minus 1 cubed equals n squared times 2n squared minus 1. To prove that this is true for all natural numbers. Okay, just like the one before. Okay, so once again, let's prove this. Let's prove this statement for n equals 1. That is, we're going to show that it's true for n equals 1. Okay, so these three terms are basically the first few terms of this parentheses, 2n minus 1 cubed. So 2n, 2 2 times 1 minus 1. Let's see, 2n, 2 minus 1, 1 cubed is that. Then plug in for n with 2, so 2 times 2, 4 minus 1, 3 cubed. For 3, that would be 2 times 3, 6 minus 1, 5 cubed. So these three are the first few generations of this expression. So to show that this is true for n equals 1, so step 1, show that that statement is true for n equals 1. Okay, so we're going to plug in 2 times 1 minus 1 cubed is equal to 1 squared times 2 times 1 squared minus 1. Let's see if it's true. So we have 2 minus 1 cubed, then we have 1, right? 1 times 2 minus 1, which is 1. So 1 equals 1. So we've shown the first step in the mathematical induction. Step 2, we're going to, using the induction hypothesis, assume using the induction hypothesis, we know that n equals k must be true. Thus, this statement then is true. So 1 plus 3 cubed plus 5 cubed plus this plus, instead of n, I'm going to replace this n with k. So you move this up a little bit, plus 2k minus 1 cubed equals k squared. Notice I'm replacing the n with k, times 2k squared minus 1. Okay, we assume that that is true. So then, step 3, we're going to use this induction hypothesis to show that n equals k plus 1 is true. So use the induction hypothesis to show that n equals k plus 1 is true. And once we do that, we've completed the mathematical induction proof of this statement. So let's do that. So we have 1 plus 3 cubed plus 5 cubed, right, plus plus 2k minus 1 cubed, right? That's the mathematical induction hypothesis. Now we have to add the k plus 1 to this side. So 2 times, instead of k plus 1 minus 1 cubed, and k plus 1 to the other side. So k plus 1 squared 2 times k plus 1 squared minus 1 close bracket. Okay, I was barely able to fit that across the page there. Okay, so now we have to simplify and see if the left-hand side and the right-hand side are equal. If they are, then we've completed the mathematical induction proof. So first of all, notice on the left, all of this is the induction hypothesis. So that is equal to that, right? So I can replace this piece, or the induction hypothesis, with its equivalent, which is shown on the right-hand side. So that's the induction hypothesis. Let's replace it. Let's replace all of that with what it's equal to. You see that? So I'm going to replace all of this with just that. We have k squared times 2k squared minus 1. Now I'm going to add this piece. Okay, so plus, let's simplify it as we write it here. So 2k, if you distribute the 2 into this, you get 2k plus 2, and then minus 1, you get 2k plus 1 cubed, right? So plus 2k plus 1 cubed. So this is the simplified version of that piece, okay? On the right, let's simplify things as much as we can. Yeah, so let's do that. So k plus 1 squared, right? That's that piece. Now let me expand this binomial squared, or the quadratic equation. Let me expand that before distributing this 2 into it. So we have 2 times k squared. I'm expanding this. K plus 1 squared, I'm expanding it. Plus 2k plus 1 minus 1 close bracket. Okay. It's all simplification after this step, right? So on the left, let's distribute this k squared into this parentheses. So we get 2 k to the 4th power minus k squared, right? Distributing this into this and then this into that. Then to expand this, let's expand this as well. 2k plus 1. We have shortcut formulas for all of this, right? So I'm just going to apply that. So plus, let me put all of that in the bracket. So this first term cubed, 2k cubed, plus 3 times 2k squared times 1. So 3 times, I'm just following the shortcut formula. If you remember it, you know exactly what I'm doing. And so 2k squared times 1. Sorry, that's just multiplication. So 3 times this term squared times 1, then plus 3 times 1 squared times 2k. Okay? And then plus, of course, plus 1 cubed, close bracket. Anything you see inside these two brackets is the expansion of that, a plus b cubed. Please look that up. It's in your book. It should be in a table either in the beginning of your book or at the end of your book. I don't remember right now where the author put it. Or you can just look at special product formulas on Google and see if it comes up. But a plus b cubed is what I've applied here. And then equals, on the right, I'm going to run out of space here, but I'll try to fit it. Maybe I can. So we have k plus 1 squared times, if you distribute this 2 into this and simplify it with this minus 1, you get 2 times 1 is 2 minus 1, 1. So you get 2k squared. Just distribute this and simplify. 2k squared plus 4k plus 2 times 1 is 2 minus 1 plus 1. Like that. Okay, so that's on the right-hand side. Okay, so we're going to take this simplification one more step further. Let's see. So okay, so I should have expanded that, but it's okay. Let me do that now. So I'm going to start here. Hopefully that'll give me more space. So 2k to the 4th power. Well, let me bring this down a little bit. So I'm going to simplify this expression a little more. 2k to the 4th minus k squared plus, right, plus 8. 2 cubed is 8, k cubed plus 8 times k cubed plus 2 squared is 4. 4 times 3 is 12. 12k times 1 is 12k, or 12k squared, sorry, because this is 2k squared. So 12k squared plus 3 times 1 squared is just 3, times 2k is 6k, plus 6k plus 1 cubed is just 1, right? On the right, we have, well, since I didn't do it up there, I should do it now. Let me expand this one. So k plus 1 squared is k squared plus 2k plus 1. And I'm just applying the shortcut formulas, or special product formulas, you may call it. 2k squared plus 4k plus 1. Okay, just taking it step by step so you can follow this work, and then hopefully this way is more clear than if I combine these steps. Okay, so let me then, the left-hand side is pretty much, well, we still can combine things here, right? Let's simplify the left and the right a little more. So 2k to the 4th is the only 2k to the 4th we have. So I'm going to write it down like that. Minus k squared plus 12k squared is plus 11k squared. I should have written that. So let me go in the descending order of power. So I'm going to put 8k cubed first, just to be in order. So plus 8k cubed, sorry about that, plus 8k cubed, plus then I'm going to put the 11k squared that I had before, plus of course 6k, which is the only k term there, plus 1, like that, equals. Now we have to multiply this by that, right? So k squared times 2k squared is 2k to the 4th power. K squared times 4k, it is plus 4k cubed, and plus k squared, right? K squared times 1 is plus k squared. Then 2k times, let's see, 2k times 2k squared is plus 4k cubed, right? We add the powers. 2 plus 1 is 3. 2 times 2 is 4. K to the 1st power times k to the 2nd power, add the powers, k cubed. Then 2k times 4 is 8k squared. So plus 8k squared. I'm definitely running out of room now. So let me just, after one more term, I'm going to come down here. Plus 2k times 1 is 2k, right? Plus 2k. So let me add here underneath it. So hopefully it's not too confusing if I come down here. Now all I'm doing is distributing this 1 into the second parentheses. We get all the three terms back, right? 1 times 2k squared is 2k squared. 1 times 4k is plus 4k. 1 times 1 is plus 1. Okay, so let's simplify. The left-hand side is already simplified, right? So let's do the same thing for the right-hand side and see if we have the same thing. So on the left, let me rewrite this. We have 2k to the 4th like that, plus 8k cubed plus 11k squared plus 6k plus 1 equals. So 2k to the 4th is the only k to the 4th term we have, 2k to the 4th. How about cubed? 4k cubed plus 4k cubed, that'll give us 8k cubed, right? So we have those taken care of. How about the k squared plus 1k squared plus 8k squared? That's 9k squared plus another 2k squared down here. We get 11k squared, right? How about k terms? 2k plus another 4k term here, that's 6k. And then 1 is the only constant on the right, so let's write it down. Okay, so if you compare the left and the right, you see that the two sides are equal. So we've proven, we have been able to prove this statement. Okay. So here, mathematical induction is complete. Okay. All right, so with this, hopefully these examples gave a little bit of insight into mathematical induction proof. Like I say, if you are not a math major, then you won't see much of this kind of proof. But for those of you who are math majors, this will definitely come up again and again. This wraps up section 12.5, and unless the coordinators change the syllabus, it is also 12.5 is the last section. At this point of time when I'm recording the videos, it is the last section in this course. And I hope that you've been able to put these videos to good use. And it's been great having you ask questions about this and having you had in my class. So good luck with this semester and have a nice day.